Welcome. In this video, we're going to take a look at how to derive the moment of inertia of a thin rod using integral calculus. All right. Moment of inertia is also called the rotational inertia of an object, and remember that it's the equivalent of the mass in something like an F equals ma. All right. So here is hopefully our thin rod. Yes. Okay. Our thin rod has a length of L, and it's got a mass of m. And we want to be able to derive the moment of inertia of this thin rod about any axis. So for instance, let's say that we want to confirm the moment of inertia for an axis through the middle of the rod at L over 2. All right, so we're going to take our x-axis and we're going to put that origin at the left-hand side of the rod, and we're going to run it all the way through the rod. So that is our x-axis. We don't need to worry about y because this rod is so thin that we assume that its width is much smaller than its length. All right. And so first we need the equation for I using integrals. So I, remember, was the sum of all of the individual masses times their distances from the axis squared. Okay, so since we can slice this rod up into an infinite number of infinitely small masses, then that suggests an integration. So really we're going to be integrating all of these little dm's, those tiny chunks of mass, times their distance from the axis squared. So remember, that's what r is, the distance from the axis of rotation. Okay, so for instance, here's a visual. We've got this little chunk of mass, dm, and it has a distance from the axis of rotation of r. All right, so we've done a derivation similar to this before when we looked at how to derive the center of mass, the location of the center of mass, and the trick was in changing that dm to a variable here that goes along with the r. So the r is a position variable, all right? So we're going to change that r to an x because we're talking about along the rod's oriented along the x-axis. And so that dm needs to be changed into something with dx. And the key here is, just like it was with the center of mass, this density element. We're going to call it sigma. So normally density is a mass per unit volume, but this is going to be a mass per unit length density because this is a really thin rod and we just assume it only has like one dimension. So instead of having a length, a width, and a height, it's just got a length. All right. And so if we want the density of just that little chunk of dm, well, it's going to have the same density as the entire rod. So it's going to have a mass of dm, and it's going to have a length, an extent along the x-axis of just a tiny little amount of x. And so that you can see then this is our key to changing dm into something with dx, because solving for dm, we get sigma dx equals dm. But what's sigma in terms of the rod? Oh, it's just the mass divided by the length. So then we have m over L dx. That's equal to our little friend dm. And that's what's going to go in to our integral here. So replacing the dm with m over L dx, and as I said, we're going to replace the r variable here with the x because we're going along the x-axis. So then our equation now becomes the integral of x squared times m over L dx. So again, replace the r with x, and we replaced the dm with m over L dx. Okay, so now the final heartache is going to be the limits of integration for our integral. And that's where my blue x-axis here is going to come into play. So I am going to make the origin, actually, of my x-axis the axis of rotation. Okay, so this is x equals 0 in my scheme of things. So then that makes this end over here negative L over 2. In terms of my x, and then this end over here is going to be positive L over 2 away from the origin. All right, so remember that your limits always come from starting of that variable to ending of that variable. So where's our starting position? It's going to be negative L over 2, and then where are we going to stop integrating? It's going to be positive L over 2. All right, so The difficulties in this: one, changing the dm into m over L dx, and I'm going to tell you for a thin rod, every single time the dm is going to change into m over L dx. So that's not going to change, which means functionally the only thing that's going to change every time is the limits of integration. All right, and so I'll discuss that in a minute. So m and L, those are constants. We can pull those out of the integral, and then that just leaves us with the integral of x squared dx. So the integral of x squared is going to be x cubed over 3, and we're going to evaluate that from negative L over 2 to L over 2. So remember, we evaluated the upper limit first. So we've got m over L. We're going to have L over 2 cubed divided by 3. And then we're going to subtract the evaluation at the lower limit. So that's going to be negative L over 2 cubed divided by 3. And then we have that m over L out front. So we can pull the 3 that's in the denominator out, and then we're going to have, let's see, m over 3L. Let's see how badly I can mangle this algebra. We got L cubed over 8 plus L cubed over 8. So that's going to give us 2L cubed over 8 times the m over 3L out front. And so, oh boy, let's do some simplifying here. We're going to end up with L squared. We got 1 and 4. So we're going to end up with 1/12 ml squared. And you can confirm that with the chart in your textbook, the table in your textbook that tells you what the rotational inertia is for a thin rod rotated about its center. 1/12 ml squared. All right. So this is something that you need to be able to do on the AP test, whatever axis they give you. So let's take a look at another example. If we want I for rotating the rod about its end, then we're going to make this our origin, and our integral is going to have different limits of integration. So it's still going to be m over L out front, but now we're going to go from starting position 0 to ending position L. All right, and then it's going to be x squared dx inside. What if they wanted it at like 1/3 of L? L over 3 is our axis of rotation. So then that's going to be same m over L out front. That's never going to change. Now we're going to go from starting position, which is here, negative L over 3, to ending position over here. That's going to be positive 2L over 3. So those are going to be our limits of integration that time. So this will allow us to find the moment of inertia for any axis of rotation for any thin rod. All right? There's no getting around it. You just have to practice this process. Practice setting it up, practice changing the dm into a dx, and then practice using the limit, figuring out what the limits of integration are. All right? That's it for this time.